Okay, this is part 2 of chapter 1. So let me share with you a couple of very practical examples of things that we experience so often in our lives that we may or may not be aware that there's optimization modeling going on behind the scenes. Anytime we buy airline tickets, boy, that's been happening for, well, decades in terms of the basic software, but it's gotten quite advanced in the past generation. We buy sporting tickets. We know that for NFL teams, baseball teams, they're dynamic ticket pricing. Heck, I went to a restaurant recently and their specials were printed out and there was no pricing on the menus. And I'm speculating that even good to fine dining restaurants are going to begin using dynamic pricing. How are they doing it? They're using some modeling to identify what they can do in terms of optimizing their revenues, while in some cases minimizing their low customer satisfaction, because they could be related. Disney has dynamic ticket pricing as well. So most of you take for granted, but if you're aware of these things, but the fact is that there are advanced modeling algorithms behind the scenes. Another example is TSA screener scheduling. And that's a personal example of mine, something I worked on in the past, in the early days of the formation of the TSA. And so the screeners are scheduled on a basis to minimize cost, but while optimizing or maximizing the throughput of passengers while maintaining that rate. Another thing that I mentioned earlier, we all take perhaps for granted is the notion of the way the internet works and the networking optimization models that go on behind the scenes in terms of the response rates you see from servers and the way the routers that are placed strategically in different forms and different sizes and capacities around what we call the internet route the messages. It's not always first in, first out. All right, so there are different optimization models. It can also be used for management of venues and locations and crowd controls. It's used at borders, Uber surge pricing, and frankly, Uber mapping in terms of allocating Uber resources to a call for an Uber resource is a function of mathematical modeling. So there are lots of things that you may not always be aware of that these are used for. Just a quick explanation, the fact that some project I worked on in the past, in the early days of the TSA, is the fact that some airports around the country are screened by private agencies. The biggest one you may not be aware of is San Francisco. If you ever fly through San Francisco, take a look at the screeners that work there. They're not TSA employees. They are privatized company employees, and that's what I worked on. I worked at San Francisco back in the early part of last decade to set up some models when screeners were just being put into place. And we had to be very careful about some of the constraints we faced, like male on male only, or screening, female on female, no mixed gender. And we had lots of data that came from the airlines, but we didn't have gender at that time. So lots of tricky things. And it's really done in a way today that the TSA themselves, the government agency, uses staffing allocation models. And as I mentioned, we optimized our models with the TSA screener scheduling to minimize wait times, but while also, for the sake of the privatized organizations, minimizing the costs to that organization because they're profit driven. Now, what we're going to be using in this course are manual methods and Excel-based methods. Reality is also that there are higher tier, more sophisticated software tools that emerge as circumstances and markets warrant. And here's an example of something that came into play in both of these from Regal Decision Systems and Sabre Corporation to determine staffing levels at a variety of functions associated with airport operations, including crew scheduling and so on. And so in early days, some of the scheduling were done, again, using Excel models. Now these more sophisticated solutions have emerged. So I want you to appreciate these tiers, from the low level to the mid level to the top level. I was just showing you something at the top level. In this course, we're going to use manual calculation methods, low level methods, if you will, for the models in terms of how to calculate that. We're also going to use what I'll call mid level generic software products like Excel that we can configure for the application. And of course, in real world, in many instances, you're going to use third-party software products that are very customized for certain applications or industries, just like I showed you from Sabre and Regal. So why do we want to use these kinds of models? Well, as I remarked with regard to pricing of airlines and events and games and so on, it affects revenues, which ultimately affects profitability. And so, but it also has a bearing on customer satisfaction in some cases, like queuing and how long we have to wait in line, right? Do we feel very good after we have to wait a long time in an airport screening line? No, not at all. And of course, it ultimately affects operations of a business in terms of how you staff it, how you run it. And who should care? Well, we as consumers, we as customers care about these things. The more we know about it, the more well armed we can be to understand circumstances we should pay attention to with regard to surge pricing, for instance, and so on Uber. And if you're in business and if you're on the selling side, you certainly want to understand it in terms of the marketing and the finance and again, all the other elements with regard to operations. So bottom line, it's really important, and hopefully you'll find something good and useful in this course that you can enjoy. All right, so let's talk about model development. And because a model is really just a representation of something else, whether it's a real object or a situation like a queuing line. And there are different types of models we can use. You can use a physical replica, let's just say a scale model of a building like the White House, or use a flight simulator. You can go with a real physical flight simulator. You can use analog models. They're physical, but like a thermometer represents temperature, a speedometer represents speed or velocity, but they don't physically resemble the object. They analog, or they present that same data in a different form. Lastly, highlighted here in yellow, and the page number I'm referencing is from the text. And the mathematical models, right? We use symbols, we use expressions, we use formulas, we use statistics, and in a lot of cases, of course, we wind up using estimates, and that's why you run through multiple models. So why do we want to use a model? Well, generally, it's going to require less time, less cost, and less risk in terms of for instance, flight simulators, you can appreciate that. And certainly with regard to modeling airport screening times and turnarounds and costs, yeah, you may do a little of experimentation with real-world circumstances and people, but you can develop a model first and then try it based on the model, and then tweak the model again based on real-world conditions as you learn and provide feedback to your model. Then you can expand and grow that model and use it in multiple situations. All right, so here's where we get into something very specific, and I really want you to understand this notion of the objective function, right? It's an expression that describes what we're trying to accomplish in terms of an objective, like maximizing profit or minimizing cost. So let's consider a simple production example. If we can make X number of units produced and sold in a given period of time, say a week, well, objective might be to maximize weekly profit. So if we say there's a profit of $10 per unit, and we say the X is the number of units produced, the objective function in this case is to maximize X, right? So we're using max and min as well, and when we use objective function expressions. Airport screening, again, if it costs $25 an hour and the number of screeners is represented by X, we may say a min, and we'll represent that at 25X. Now, another important element are constraints. These are restrictions or limitations or requirements. There are so many possibilities here. So that's the first sub-bullet here. If we had a production capacity constraint, we might say, well, we need a certain number of hours to produce a given unit, and for X. And there's only 40 hours available per week because we only have a certain number of machines. Then we would express a capacity constraint as 5X is less than or equal to 40, right? Because we need 5 hours to produce a given X, we've only got 40. Therefore, the reality is that maximum value that X can equal is 8, right? So another example, sometimes we can only, or another basis for that, sometimes only one machine can be assigned to each job, or the only machine can have only one job at a time, or it can only be operating for a certain number of hours a day, so on and so forth. Again, there are lots of possible constraints. And I'll be giving you examples for the sake of our problems. For the most part, I'll defining constraints for you. There will be a problem or two on a given test where you're going to have to interpret the language to identify the constraints. Now, when we have certain types of constraints, it's important for us to understand whether or not they are controllable or uncontrollable. So, for instance, if the decision maker says, well, the profit's $10, that's under the control probably of someone else. Now, we could quibble about whether or not it's actually under our control, maybe indirect. It depends on the breadth of your decision-maker group. So, again, nominally, some of these things could be changed, but we have to identify whether you could directly change them. We've got to be able to specify these things before we make a solution, develop the model and recommend a decision and a solution. Another really important parameter to understand is the notion of decision variables. Now, these are the controllable inputs for the model, that X, if you will, right? Really easy to flag A, B, and C. We often denote, if you will, as variables X, Y, and Z. And I'll be using those types of conventions. So in that model we were talking about in terms of the number of production quantity or for screeners, we just called it X. And that's the decision variable. How many screeners to schedule. Right? That's what we're trying to devise and determine. Now, we decide whether or not we have a deterministic or probabilistic model based on whether or not we know all the inputs to the model and if they can or cannot vary. Now, the reality is most things in life are probabilistic. And so they are more difficult to work on. And so, again, if the number of airline departures could be varied, the model would have to be stochastic or probabilistic. So it's important for us to understand that because that in turn will potentially affect the way we arrive at our solution. Now, something that's really important when you're developing models and executing them for real-world representation is to understand where your data comes from and how you structure it and how well you manage it. There could be a lot of different decision variables that I just mentioned and talked about constraints. In the case of the screeners, we had a dozen decision variables, and at different times we would have anywhere from 25 to 35 constraints. And we hit thousands of data elements, and it was pretty unwieldy initially using Excel for this, but we managed and we structured it until the emergence of those third-party software products, the more sophisticated products that met the market need a little more flexibly and easily. Now, this is also something really important when we think about the solutions, right? The best solution. So the mathematically best solution in output is what we call the optimal solution. And secondly, if we have a choice where we can't satisfy all of the constraints, we refer to that as being infeasible. Infeasible, regardless of whether or not it gives us a value or a solution that is maybe desirable, but we still refer to it as infeasible. And we're going to say, for the sake of our course, the idea that only a solution that satisfies all of the constraints that is feasible would be a candidate for the best solution. I mention this again because you could take different alternatives and twist it and turn it and have an infeasible solution, and someone says, well, we can change a variable and make it feasible. Okay, maybe you can, but then you're really changing the model. So let's understand that we have the optimal solution is what's the most desirable, the mathematically best output, and that optimal solution has to be comprised of an alternative or from an alternative that satisfies all the constraints. All right, we're going to stop there for part 2, and I'll go on to part 3 with a different file.